Okay, let me go into, let's see what I'm writing here. Okay, bit of an angle, isn't it? That's all right. So the 2 pi's cancel out, right? And so you're left with the reciprocal of that, which, you know, are you going to use a calculator to compute that, or are you going to do it by hand? In which case, you know, you'd say it's, well, let's use a calculator, shall we? So I'm going to go to GeoGebra just to do that one little calculation. And where is the, here we go. So we've got, oh, and we're way zoomed in here, so let's zoom out a bit. Oh, well, we're not going to do any graphing anyway. I'm just going to say, what is the reciprocal of 9.15? And that is 0.11. You might have guessed, huh? Maybe we need more digits, huh? Yeah, so 0.1093. Okay. So we'd go, oops, I don't want that. 0.1093. So I'm going to turn this off and go back here and say this is 0.1093 times 10 to the negative 7th, right? Because it's the reciprocal of 10 to the 7th, right? Which in scientific notation, you'd multiply this by 10 and divide that by 10. You'd say I got 1.093 times 10 to the negative 8th, right? And that is the wavelength. The reciprocal of that is the frequency, right? This was, by the way, an approximation at this stage. I should use the approximation symbol to indicate that. So that's the wavelength. The frequency is then the reciprocal of that, which we know what the reciprocal is because that's what we started with, right? So the frequency is 9.15 times 10 to the 7th. So that's 91 million oscillations per second. That's, you know, high frequency, right? Makes for high fidelity sound. Okay, and what else do they want to know? That's it. Okay. If we wanted to sketch a graph of this, well, we'd kind of have to know what A is, right? So I'm going to sort of scoot this over a notch, make it look a little bit more. Okay. So back to the book. We've got blood pressure, mass spring system. Okay, let's get into the review. Well, I kind of like the Ferris wheel. Ferris wheel has a radius of 10 meters and the bottom of the wheel passes 1 meter above the ground. The Ferris wheel makes one complete revolution every 20 seconds. Find an equation that gives the height above the ground of a person on the Ferris wheel as a function of time. Okay, so I'm going to draw a picture. And I guess I'll use my compass for this situation. Notice the radius is 10 meters, okay? So, sorry. Where is my compass? So, whoops. 10 meters, huh? Now, let's see, I suppose we could say that's 5 centimeters, right? Which would be about like that, okay. So here's our Ferris wheel. Ooh, it's a large Ferris wheel. Well, 10 meters, okay. And so if we mark off centimeters in here, each centimeter will be 2 meters, right? So let's say here's 2, 4, 6, 8, 10, and it's 1 meter above the ground, right? So this is where I'm going to put my x-axis is going to be the ground. And well, this should be 5 here, right? And let's extend the y-axis. Okay. I don't quite have it all. Okay. There we go. Well, doesn't quite fit, does it? I'll zoom out a notch. Okay. So this is 1, 2, 3. Oh, those were 2s, weren't they? Oh. 5, 6. Wait, what did I do? Okay, so these are half centimeters. 1, 2, 3, 4, 5. Sorry. Well, let's just mark off our half centimeters, shall we? They're kind of hard to see, I guess, is the problem. Yeah, and it's actually more than a half a centimeter. That's another part of the problem. I have a solution to this problem. We just start all over again. Okay. Is this 5 centimeters in the first place? Yeah, pretty much. Okay. So, and then I think maybe we can kind of use the rules on the paper as so 1, 2, 3, 4, 5, 6. No. Okay. So this is sort of bottom to top is 10 centimeters. So every half centimeter should be a unit. I'll tell you what, I'm going to just mark every centimeter and then I'll eyeball the halfway points because it's kind of hard to see what's a half a centimeter on here. Okay, so let's say that's halfway. Perfectly evenly spaced. Yeah. And so we want to go a half centimeter down here, right? That's going to take us to the ground. Which is here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which should be the center, right? 12, 13, 15, 16, 17, 18, 19, 20, 21 meters to get to the top. Phew, that was a bit of an ordeal. Okay, so this is the center point. Okay, and this is the ground. All right. So here's the deal. We want to take our unit circle, magnify it by a factor of 10, and then shift it up 11. Okay, so the center of the circle is here. To get to a point on the circle, we have to go to the center and then rotate around a distance, right? So I'm going to say, look, we've got the x coordinate here is 10 times cosine of t. And the y coordinate, and this is the trickier one, right? It's going to be 11 plus 10 times the sine of t. Do you see that does the job for us? So this 11 is shifting up by 11. And this 10, see, if you're on the unit circle, we'd have x equals cosine t and y equals sine t, right? So we do two transformations, right? We shift, well, we first stretch both vertically and horizontally by a factor of 10. So that's x equals 10 cosine t, y equals 10 sine t. That takes us to a point on a circle of radius 10 centered at the origin, right? And then by shifting up 11, we get our Ferris wheel. So where are we starting though? Ferris wheel has a radius of 10 meters and the bottom of the wheel passes 1 meter above the ground. The Ferris wheel makes one complete revolution every 20 seconds. Find an equation that gives the height of the ground of a person. So where does the person get on the Ferris wheel? The person gets on the Ferris wheel at the bottom. Oh, well, that presents another problem, right? Which is when t equals 0 here, we'd be at x equals 10, y equals 11. That's over here, right? So we put 10 on the x-axis here. Right, that corresponds to this position. So if you were to plug in t equals 0 here, you'd be starting here, but there's no place, you can't get on the Ferris wheel at a place like this. You get on the Ferris wheel down here. So what we can do to fix this is to say, I'm going to swap these guys, right? And subtract. So I'm going to modify this, okay? I'm going to say, yeah, x is going to be the sine. So it starts at 0. When t equals 0, x is 0, we're at the bottom of the Ferris wheel. Y is going to be the cosine. So this is going to be 11, but I'm going to put minus 10 times the cosine of t. Do you see why the minus works? Because when t equals 0, cosine of 0 is 1. 11 minus 10 is 1. So we start at this position, the vertical position of y equals 1 meter above the ground. It's where we board the Ferris wheel. And then which way does the Ferris wheel go? Does it go around clockwise or counterclockwise? Well, that's a good question. So let's make a table of values and see if this is our model, then which way are we going to go? Okay, so here's t, here's x, and here's y. Oh, sorry, in the margins here. And let me write it, my formulas up here. I've got x equals 10 cosine t, and y equals 11 minus sine t. And let's use those to tabulate our position on the Ferris wheel. And we don't have to pick, the usual suspects, pi over 6 and pi over 4. We could just pick pi over 2, right? That'll indicate where we're going, right? So we start out 0. Cosine is, oh, sorry. I miswrote. X is the sine here, right? And y is the cosine, because we're starting at the bottom. Okay, so when t is 0, x is the sine of 0, which is 0, and so we start right there. And y, oh, I forgot the 10. Absent-minded. That's the amplitude of oscillation. 10 is amplitude. Okay. So now when t equals 0, that's my starting time. cosine of 0 is 1, 10 times 1 is 10, 11 minus 10 is 1. Okay, so let's say we're at t equals pi over 2. Yeah, we haven't used the frequency yet. So when t equals pi over 2, we'll put in a multiplier to fix that, okay? But let's just first see where are we at, a quarter turn, right? When t equals pi over 2, we're at a quarter turn. Sine of pi over 2 is 1, so this is going to be 10. And cosine of pi over 2 is 0, so this is going to be 11. So where are we? We're here, right? X is 10 and y is 11. Top of the thing. Okay. And so we're going around counterclockwise. So you can see when t equals pi, we'll be at 0, 21, right? Why? Well, cosine of pi is -1, so 11 minus -10 is 21, right? 3 pi over 2 will take us back in the negative direction here. Sine of 3 pi over 2 is -1, so this will be -10. And this will be 11. And then at 2 pi, we're back to where we started. But we want it to be not 2 pi per revolution, but they say 20 seconds. So we want to multiply the input by omega, right? So here's our final tweak of our functions here. We're going to say x is equal to 10 sine omega t. So we'd like to choose omega so that our frequency of oscillation is 1 cycle every 20 seconds. And this is 11 minus 10 cosine omega t. So we'd like to say as t goes from 0 to 2 pi, we would like omega t to go from 0 to 20. So that looks like omega should be 10 over pi. What happened to the chat? Oh, okay. Okay, so that will do it then. That's our final version of this thing. So now, let's put our table in here, okay? So if we're using x equals 10 sine and omega is 10 over pi. So y is going to be 11 minus the cosine of 10t over pi. So with these two functions, yeah, we start at the same place, 1 meter above the ground. When t equals 0, sine of 0 is 0. That's x. Cosine of 0 is, oh, sorry, I forgot the 10 here. So easy to forget things, isn't it? Especially when there isn't much room. So this is 11 minus 10 cosine. Is that illegible enough? Yeah, I'll rewrite it over here. So x is 10 times the sine of 10 over pi t, omega t, and y is 11 minus 10 times the cosine of 10 over pi t. Okay. So now, what's a quarter turn? Well, it should be 5 seconds, right? 1/4 of 20 is 5. So let's say when t is 5, what do we got here? Wow, this is so wrong. Is it the the reciprocal or something. Okay, so we want omega to say when t is 2 pi, we want to choose omega so that omega t equals 20 when t is 2 pi. So that's going to be pi over 10. I just have the reciprocal, don't I? So this is the, yeah, it should be pi over 10. Yeah, okay, obviously, right? So when t is 20, this would be 2 pi. Is that what you were thinking? You were wondering why I was doing this the wrong way about? Okay, well, let's fix these guys. So this is pi t over 10, pi t over 10, and this is pi over 10, and this is pi over 10. Okay, so now when I plug in the 5, I get pi over 10 times 5 is pi over 2, sine of pi over 2. It's exactly what we had over here, right? 10, and we'll get cosine of pi over 2 is 0. 11 minus 0 is 11. Okay, so when we go to 2/4 turns, we'll be back here at 0 because what? Sine of pi is 0. Cosine of pi is -1, so we're at the top of the world, right? 11 minus -10. And then at 15 seconds, we'll be back at -10, 10 to the left, 10 meters to the left, and 11. And at 20, we'll be back to where we started, right? So find an equation that gives the height above the ground. Okay, so the height above the ground is y, right? So the answer to their question is y, well, this is almost it here. Y is pi over 10 t, right? That'll give the height above the ground at time t. This gives your horizontal position as well, but they didn't ask for that, right? They just asked for the height. And so our line of equilibrium is 11. And so if we were to plot this, horizontally, let's do that quickly here. I'm just doing a rough sketch. Why is it? Oh, I see the cord is a little short. Okay. So we got 5, 10, 15, 20, perfectly evenly spaced. This is t in seconds. This is the height. And we see that we're gonna have, we want to go up to, 21, huh? So let's say here's 5, 10, 15, 20, 21 will be here. So the line of equilibrium is at 11. Let's say that's here. And we're going to start at a trough, right? 11 minus 10 is 1. So we start 1 meter above the ground here. After 5 seconds, we're at equilibrium. After 10 seconds, we're at the maximum height, which is 21 meters. And let's plot that point here. And then at 15 seconds, we're back at so-called equilibrium. And then we're back to the launching pad, right? And here's our sinusoidal curve, which is actually a cosine or a negative cosine curve here. Okay. And obviously, as you keep going around you'll keep oscillating in that same fashion, right? But this would be the function that describes your height above the ground as a function of t, where you're on a Ferris wheel of radius 10 meters. You board the Ferris wheel 1 meter above the ground, and it takes 20 seconds to go around. Okay, you can see why I like the Ferris wheel problem, even though I made a bit of a botch of solving it for you. Let's then get into the review questions. Okay, and let me make sure I've got this. Oh, the Doppler effect, that's good. There's some good stuff in here. But let's go to the review. So in the review, we want to make sure we understand what a terminal point is. So chapter 5, concepts. So the unit circle is a central concept. So yeah, so let me write these out, and I'll just sort of read from the book. You can also refer to the book. But the unit circle is the solution to the equation that says x squared plus y squared equals 1. That is, the distance from a point on the circle to the origin is 1 unit, right? You could also think of this as 1 squared, but that will work, right? So the terminal point P, whose coordinates are x and y, determined by, this was actually straight from the book, traveling a distance t counterclockwise around the circle from 1, 0, the x-intercept. Yeah, this leads to x is the cosine of t, and y, and these are actually definitions, right? This is how we define the cosine and sine functions. Yeah. So what are some special terminal points? Special terminal points. And let's make a table, okay? And we'll just do it in the first quadrant, right? But so we start here. So if you don't travel any distance at all, then you're at 1, 0, right? Cosine is 1, sine is 0. If you go pi over 6, then x is reduced to square root of 3 over 2, and y is increased to 1/2. If you go pi over 4, then x and y are the same, square root of 2 over 2. At pi over 3, x is 1/2, and y is square root of 3 over 2. And if you go to pi over 2, then you're at 0, 1, right? And these repeat in the other 4 quadrants with the appropriate sign, SIGN sign, for both x and y, right? Okay. We have the reciprocal identities. what secant of t is the reciprocal of cosine. Cosecant of t is the reciprocal of sine. And tangent, well, I guess cotangent, right? We haven't really brought up what tangent is. Tangent is the ratio of y to x, right? So shall I do that over here? Cosine of t is the ratio of x to 1. Sine of t is the ratio of y to 1. And tangent of t is the ratio of y to x. So why talk about cosine and sine as ratios rather than just simply x and y? Well, it's to be sort of consistent. All of these can be thought of as ratios. Not sure why the lighting is a little funky, huh? Okay. So then the reciprocal functions over here, secant, cosecant, and cotangent give you the 6 trig functions, right? Okay, so the Pythagorean identities, these are huge. So Pythagorean identities are, well, it comes from x squared plus y squared equals 1, where x is cosine and y is sine, right? So you've got cosine squared t plus sine squared t, regardless of what t is, that will always be 1. If you divide through by cosine squared, you get 1 plus sine over cosine is tangent, here squared, right? Because we're dividing by cosine squared. And the reciprocal of cosine is secant. So you get that form of the Pythagorean identity. If you divide through by sine, you get cotangent squared plus 1, to sine squared. We're dividing through by sine squared. And so those are the 3 basic forms of the Pythagorean identity. There are the even-odd properties, shall we call them? Which says that cosine is even and sine is odd. So cosine of a negative value is the same as the cosine of the opposite, right? Oops. And sine of the opposite is the opposite of the sine. Same thing with tangent. So tangent and sine are odd, whereas cosine is even. So secant is also even. It's just the reciprocal of cosine, right? And cosecant is also odd. It's the reciprocal of sine. And cotangent is also odd. It's the reciprocal of tangent. Okay. So the period sine of t, so should we talk about periodicity? Sine of t plus 2 pi is the same as sine of t. Cosine, so you're going once around, you're at a coterminal point, right? Going once around the unit circle, that's going to take you back to where you started. And same thing for tangent, except tangent is kind of interesting. Its period is only pi, right? Because once you get to the 4th quadrant, you've got y and x both negative. So the ratio of negative y to negative x is the same as the ratio of y to x. So I could say the same for secant and cosecant and cotangent, right? So that's periodicity. And so the graphs, what do the graphs look like? Well, so let's just make a quick graph here, huh? So I'm going to call that the t-axis. Now, sometimes confusingly, it's called the x-axis. But, you know, x is a point on the unit circle, right? Which we haven't drawn the unit circle. Let's do that in a minute here. But so 2 pi is 1 wavelength. So here's half of that, and here's a quarter of that, 3/4 of that. And for sine, we're going to oscillate between 1 and -1, huh? So we're going to go where it started equilibrium, go to maximum displacement, back to equilibrium, the trough, and 1 complete waveform of sine looks like that. Cosine is out of phase, right? And so it looks like this. So this is sine, and this is cosine. So we have a quick look at the unit circle here. Unit circle, which, you know, we see over and over again in here, huh? Let's make it big so we can really see it. And there's a lot to see in here, right? So if we go out a distance t, so that, you know, this arc length here is t, then we end up at a point here, which is cosine t, sine t, right? And let's draw the line through the origin from that point. We can say here, this is the point where we've gone an additional distance pi, right? So this is the point with coordinates cosine of t plus pi, sine of t plus pi. And that points out, you know, sort of a reduction formula. So cosine, so this is equal to negative cosine of t, right? Because we're on the opposite side of the circle, right? So this is negative x, and this is x, right? And same thing with y, right? This is negative y corresponding to this value of y. Right? So this is negative cosine t, comma negative sine t. What if you were to go a quarter turn? So this should be a right angle here. So here's a right angle. So now this length here is pi over 2, right? A quarter turn. And so this is the point with coordinates cosine of t plus pi over 2, sine of t plus pi over 2. And what do you see? Well, you see that this is going to be negative sine t, and this is going to be cosine of t. A strange sort of reflection. And so what is this is then going to be the opposite of that, right? So this is going to be sine of t, which is, you know, this distance here, right? So this is the same length as this. So that's sine of t, that's positive, right? The x-coordinate is positive, and this is negative cosine of t, the opposite of what's over here, right? Did I make it too large? It doesn't quite fit on the, okay. So you can, let's just leave it at that for now, okay? So we're moving on to transformations. So let's talk about transformations. So, you know, you've got vertical and horizontal compression expansion and vertical and horizontal shifting, right? So y equals d plus a times the sine of omega t plus phi, sometimes we call that. And this is a transformation of y equals sine t by what? Shift. Well, should we want to talk? Let's talk about compressing first, right? So, or expanding, right? So we can stretch. I misspelled stretch. Must be stretched to my limit here. Oh, it's a bad eraser. Stretch vertically by what? I'm going to assume A is bigger than 1, right? So if A were less than 1, that would be a shrink. So let me just put in here. It could be that, in fact, you're shrinking vertically by A between 0 and 1, right? 2, shift vertically by D, right? That's so the new line of equilibrium is the line y equals D. Then you're going to have stretch horizontally, or should we say shrink horizontally? By omega between 0 and 1. Now, if omega is negative, then we also have reflection across the y-axis, but this could also be a stretch if omega is bigger than 1. And finally, shift horizontally by what? This, you got to do a little bit of algebra to see that it's by negative phi over omega. Right? When you factor out the omega here, you'll have t plus phi over omega, and that would then be a shift to the left. Okay, so when you put that all together in the form of a graph, let's do that. So transformation of your basic sine graph. And let's say that this is our horizontal shift. So I'm going to say that this is negative, what was it, phi over omega. And, you know, you don't always use the symbol phi. It is common to use phi for this phase shift, but then we're going to go one wavelength to the right of that, which is going to be this starting value plus 2 pi over omega. And then here's our equilibrium line. And we'll have an amplitude up and down from there, right? So you've got your equilibrium up amplitude and your equilibrium down in amplitude, right? So you started equilibrium and you ended equilibrium for a sine graph, right? Halfway through, which is going to be at negative phi over omega plus pi over omega. That's half of 2 pi over omega, so half a wavelength. you're going to be at equilibrium. At a quarter of the wavelength, which is going to be what, this negative phi over omega plus pi over twice omega, that's a quarter wave shift. You're going to be here at a peak, and halfway here will be negative pi over omega plus 3 pi over twice omega. Oh, great, right in the middle of my label. Bad planning. I get this waveform. So this is the graph of y equals d plus a times the sine of omega t plus phi. If it were a cosine, what would you do? You'd start at the top instead of at equilibrium, and you'd end at the top with the same sort of shape in between, except, yeah, shifted. All right, and the inverse trig functions. There's a lot in this chapter, isn't there? Inverse trig. For sine of t, restrict domain to the interval from negative pi over 2 to pi over 2, so that the range of the inverse sine, which is denoted like so, that's not the reciprocal, right? Oh, in fact, we should include the endpoints here, right? So yeah, so if this is the domain of the function, then that's also the range of the inverse function, right? And for cosine, we're going to restrict the domain. And the reason for this is, right, so it's 1 to 1, right? From 0 to pi, so that the range of the arc cosine, which is alternately denoted arc cosine or inverse cosine, like so, is also this interval from 0 to pi, where it will be 1 to 1, right? So for tangent t, restrict the domain to the interval, not including the endpoints now, because those are vertical asymptotes, right? So the graphs of those, let's talk about the graphs, right? So if you've got, well, it's always a question as to what you should call the variables, right? So if you have y equals the inverse sine of x, sort of using generic input and output variables, then your table of values would look like what? Sine of 0 is 0, so the inverse sine of 0 is 0. Sine of what's a convenient point in between? How about pi over 6 equals 1/2, right? So the inverse sine of 1/2 is pi over 6. And plus or minus here, right? Square root 3 over 2, that would be plus or minus pi over 3. And then plus or minus 1, the inverse is plus or minus pi over 2. And so what does the graph look like? Well, it's going to be centered around the origin, right? and it should be symmetric about the line y equals x. And the output here is pi over 2. That's pretty close to 1.5, right? So I'm going to say here's 1.5, and here's 1, and so the angle whose sine is 1 is pi over 2, and the angle whose sine is negative 1 is negative pi over 2. Here's negative pi over 2. So the graph looks like this. Right? And if you were to continue on, it would form a sine wave snaking up and down like so, right? But then it wouldn't be 1-to-1, right? So this is the portion of the curve that's 1-to-1. Okay. And if you look at sine, it's going to be, the reflection of that across the line y equals x. How about secant and no dogs on campus? How about the graphs of tangent and secant? Did we do those yet? So negative pi over 2, that's a vertical asymptote. Pi over 2, that's a vertical asymptote. In between 0 and negative pi over 4, you got negative 1. Positive pi over 4, you got positive 1. Make a quick sketch of that. So here is negative pi over 2, let's say. That's a vertical asymptote. And here's pi over 2, that's a vertical asymptote. And let's say here's 1 and negative 1. So here's pi over 4 and negative pi over 4. And the curve looks like this. Right? Now think about transformations on that, right? So this is the graph of y equals tan x. And it's periodic, right? So this is one waveform. The wavelength is pi, going from negative pi over 2 to pi over 2. And how about secant? Well, that's the reciprocal of cosine, right? So to get a complete waveform, you might want to go from, say, negative pi to pi, or you could go from 0 to 2 pi. And the halfway point would be pi, and pi over 2, 3 pi over 2. So the reciprocal of 1 is 1. The reciprocal of 0 is a vertical asymptote. The reciprocal of negative 1 is negative 1. The reciprocal of 0 is a vertical asymptote. And the reciprocal of 1 is 1. So if we were to draw that out here, we'd see here's 2 pi on the x-axis. Here's the y-axis. We've got a vertical asymptote at pi over 2. And another vertical asymptote at 3 pi over 2, which are going to be there and there. And reciprocal of 1 is 1. It's going to follow this up. It's actually, it's going to be over here, right? And so here's negative 1. That's a local maximum. And it comes up and goes down like this. And over here, it's periodic, right? So it's going to continue on in that same fashion. Again, think about the transformations, right? So what's a wavelength? And we've got just a few minutes here to look over what was on the exam that was posted. So let's take a quick gander at that. So on the circle at right, I don't see a circle at right. So imagine a circle over here where there's an arc length AB subtending a central angle of theta. What is the reference number T bar for this T? This is not 30 degrees, right? This is 30, distance of 30. So let's go ahead and well, let's see. Can we have another form of this? I just want to go to here. Oh, and here, and open up the solutions. I think in the solutions we'll see the right thing, right? Oh, this is a different problem, isn't it? Okay. We'll try to post the right thing. Um, I don't know. Do we need to take another day for review? There's so much material in here. It just kind of blows my mind. What can I say? How you must feel, I don't know. We do need to get on to chapter 6, but I think, chapter 5 sort of encapsulates so much of the essence of trigonometry. I don't know. We could take another day to review. I'm especially now that I'm realizing I posted the solutions to a different exam, right? That's kind of awkward, isn't it? I don't know. Well, I'm not getting any, usually when I say, should we postpone, there'll be a clamoring of yeses.
Yeah, I think we would appreciate another day.
There we go. That's better. I'd like to review more, says Jadzia. Yes, says Mary. Okay, I hear you. Yeah, I mean, I've been going pretty fast here and realizing, God, there's so much material. I don't know how we would, yeah. So let's do that. But yeah, so here is, a similar test question. If the arc length 26 pi over 3 is traced counterclockwise along the unit circle from 1, 0, then what is the reference number for that terminal point? Well, so you go to the terminal point, which is how many revolutions is that? Oh, well, how many 2 pi's are there in 26 pi over 3? Well, 3 goes into 26 8 times. Is that right? With the remainder of 2 pi over 3? Yeah. So let me write that out for you. Um, sorry, got to find my paper. So if you've got 26 pi over 3, that's 8 pi, which is 24 pi over 3, plus 2 pi over 3, right? So this is the terminal point on the unit circle, right? And if we count by pi over 6 on the unit circle, we're here. This is pi over 6. This is pi over 3. 2 pi over 6, 3 pi over 6 is pi over 2. 4 pi over 6 is 2 pi over 3, right? So you end up here. And so that's the terminal point, but T bar is going to be this length here, right? So T bar is in fact pi over 3. Yeah. And I guess the reflection is part of the problem here, huh? If I come back on the other side, I can avoid that reflection. And have other problems. I don't know. Yeah, so so for this distance traveled counterclockwise or around the unit circle, it takes us around 4 times, right? 4 times 2 pi, and then another 2 pi over 3 takes us to here, where the reference number is pi over 3. And what else do they want to know? What are the coordinates for that terminal point? Well, this should be a familiar place, right? This is well, the cosine of 26 pi over 3 is going to be the same as the cosine of 2 pi over 3, right? The coterminal, which is negative 1/2. And the sine of 26 pi over 3 is going to be the same as the sine of the coterminal point, which is positive square root of 3 over 2. So what good is the reference number here? Basically, it says if I were in the first quadrant, I'd be at positive 1/2 square root of 3 over 2 for x and y. But I'm in the second quadrant, so I know x is negative and y is positive. That's the way they encourage you to think about this, right? Okay, well, we are out of time, but I see a couple more people have chimed in with an affirmation that yes, we will test on Wednesday for chapter 5. And then we'll start chapter 6 on Thursday. So we're still meeting the description of the week 12 module. And we'll take up with looking at some old chapter 5 problems and their solutions, which I'll try to have them match up, okay? I thought that these were matched, but apparently I was mistaken. Right, because number 2 here is negative 15/17, 8/17, whereas number 2 here, oh, well, those do match, huh? Okay. So plot that point on the unit circle. Is that what I've done here? Yeah. Here it is. Right, negative 15/17, 8/17 is a point right about there. How do you know? Well, use a calculator to approximate negative 15/17. 8/17 is pretty close to a half, right? So you can see the y coordinate is just a shy less than a half, right? And the corresponding x coordinate, then you kind of eyeball it here, and it looks like about negative 0.85 or something. Negative 0.88, it turns out, right? Okay, well, I'm 3 minutes over here, so I'll wrap it up here, and we'll continue on with this review. Mañana,
Thank you.
por favor. Yeah, question? Okay.
Thank you, Professor.
You bet. So keep up the good study. I'll, like I say, I'll try to post the problems that match up better. Looks like there was some overlap between these exams, but there's some slight variation. This is November 3rd of 2016, huh? And does this one have a date? November 23rd of 2016. I see. Oh, this is chapter 6. Oh, weird. So I must have written over the, oh, okay. Sorry, I'll try to sort this out for you. Okay, well, I guess I'm expected in my office, so I'll disappear here and reappear there and talk to you later. Wish you a pleasant afternoon.